Hi, good morning. In this session, we are going to discuss about the concept of logical quantifiers. In previous sessions, we had discussed about the concept of propositions, and basic concept of propositional logic, and how we can make arguments and validity of arguments, etc. So we are going one step further to the concept of logical quantifiers. First, let us discuss about the concept of logical quantifiers. So first, we define the concept of open statement. A declarative statement is open if it contains one or more variables, and if it is not a statement, but it becomes a statement when the variables in it are replaced by certain allowable choices. So, in the while we're discussing about propositions or logical statements, we come across statements like x plus 2 is equal to 5, and the truth value of this particular expression uh, depends on the value of x. And we mentioned that this is not a statement, or it is not a proposition, and it contains a variable x. X is a variable, and x can take different values. Maybe x can take values from the set of all integers, or it can take values from the set of all real numbers or natural numbers, or it can even take values from set of all complex numbers, or so on. So for some particular values of x, this equation or this statement x plus 2 is equal to 5 is true. And in that situation, that is when, in this particular case, when x is equal to 3, the expression x plus 2 is equal to 5 become a statement, and it is 3 plus 2 is equal to 5, and that is true. And when x is equal to 10, we have 10 plus 2 is equal to 5. That's again a statement, and it is a false statement. It is false, and this one is true. Anyhow, in both the cases, when x takes some particular values, it becomes a statement. So that kind of expressions is known as an open statement. Open statement. Actually, it is not a statement, but become a statement when the variables are replaced with uh, a value from, say, from its domain. So here some examples are given. The number x plus 2 is an even integer. As it contains a variable, so it is not a statement, but we can replace the value of x with some other values. So if x is equal to 1, then the number 1 plus 2 is an even integer. That's a false statement. And if x is equal to, say, 10, then 10 plus 2 is equal to 12 is an even integer. That's a true statement. In a similar way, the number x minus y is positive, and the validity or the truth value of this particular expression depends on the value of x as well as y, and it contains two variables. X is a variable and y is another variable, and the truth value of this expression depends on the value of x and y. Anyway, these kind of expressions are known as open statements. Now, universe of discourse. There is the set of allowable choices is known as the universe of discourse, or simply we call it as the universe. So in the previous example, the number x plus 2 is an even integer. We can take the universe of discourse as the set of all positive integers, and we can check whether x plus 2 is an even integer, is true or false for each choice of x. And in the same open statement, we can take the universe of discourse as the set of all integers, set of all positive integers, set of all integers, set of all real numbers, set of all complex numbers. All these kind of universe of discourse for the same open statement is possible. And in the case of x minus y is positive, our universe of discourse is something like set of all x y such that 0 less than x less than infinity and 0 less than y less than infinity, or it can be something like r square, or it can be something like n cross n. All these are possible um, universe of discourse for the open statement q of xy. So the same statement or open statement can have a different universe of discourse. Now we are going to our main concept. That the first one is existential quantifier. The formal definition: the statement p of x, open statement that contains a variable, is true for some values of x in the universe of discourse. Then we can write for some x p of x in literature form. Therefore, some x p of x. That is, for some x p of x is true. And obviously, negation p of x is also true for some x. Symbolically, this particular case we write as there exists x p of x. There exists x p of x. So this means there exists an x which satisfy or which make the open statement p of x true. So in our previous example, x plus 2 is even if it is our p of x. Then if our universe of discourse is the set of all real numbers, then we can write there exists x p of x, because there exists x is equal to say 2 in the set of all real numbers such that x plus 2 is an even number. So this is the existential quantifier. The existential quantifier is true, or the statement there exists x p of x is true whenever there exists at least one x which satisfies the statement open statement p of x, or which make the open statement p of x true. So here in this particular case, x plus 2 is even. The statement x plus 2 is even is true for a number of choices of x. When x is equal to 0, the statement is true. X is equal to 2, the statement is true. X is equal to 4, the statement is true. So there are infinitely many choices of x for which the statement p of x become true. But that is not necessary if you consider another statement q of x as x plus 3 is equal to 5. Then there exists x, if our universe of discourse is the set of all real numbers, then there exists x p of x is true, because there exists a number x is equal to 2 which belongs to our universe of discourse, that is set of all real numbers, which satisfy or which make the statement x plus 3 is equal to 5 a true statement. So the existential quantifier there exists x p of x is a true statement. So that is how we check whether an existential statement or quantified statement is true or false. So our next universal quantifier is for all. So it is, we consider a statement. Here we have a open statement which contains two variables x and y, and x plus y the whole square is equal to x square plus 2xy plus y square. That is a statement which contains two variables x and y, and we know that it is true for all values of x and y. It is taken from the universe of discourse, maybe the set of all real numbers or the set of all complex numbers. For all these cases, this expression is true, and this case can be symbolically written as for all x and for all y. For all x in the universe and for all y in the universe, the statement q of x y is true. So when we have such a statement for all x, so in simple case, for all x p of x, it means for all values of x in the universe, for all values of x in the universe of discourse, the statement p of x is true. So if you consider a statement like p of x, which says um, 2x plus 4 is even, and our universe of discourse is the set of all integers, then it is true for all choices of x. For any integer x, 2x plus 4 is an even number. So we can write for all x, p of x is true. But remember one thing, if we change the universe of discourse, then the truth value of the universal quantifier become or will change. Anyway, if we make a universe discourse, universal quantifier, then it is true, it has a truth value when for all choices of its variables, the statement, the open statement is true. If we can find out at least one choice of variable for which the statement is false, then the truth value of for all x p of x or for all x p of x y is false. Now, the statement for all x p of x, for all x, for all y q of x y can be written simply for all x comma y q of x y. So these two expressions are valid. Now we can define the concept of free and bounded variable. So let's illustrate the concept with the example. Consider the statement the number x plus 2 is an even number. Then the truth value of p of x varies as the variable x takes different values in the universe. When x is equal to 4, it is true. When x is equal to 5, it is false. The truth value depends on the value of the variable x. Such variable is known as free variable. So there exists x p of x, then even if it contains a variable, the truth value of this statement does not depends on the variable. So such variables are known as bounded variable. So there exists x p of x is true when there exists at least one value in the universe of discourse for which p of x is true, and it does not depends on the value of x. It depends on the universe of discourse and the statement p of x, and it is not depends on the value of x. For x is equal to 5, we cannot say something about there exists x p of x, or for x is equal to 4, we cannot make any conclusion about the truth value of there exists x p of x. So the truth value of this particular statement depends on the universe and what the statement p of x is. So in that case, the variable x is known as a bounded variable. It's bounded by the existential quantifier. And in the first case, the number x plus 2 is an even number. That's a statement, and the truth value of the statement clearly depends on this, or it is an open statement and the truth value depends on the value of x. For a particular x it is true and for some other x it is false. Such a variable is known as a free variable. Now, logical equivalent of two open statements. We already discussed about the logical equivalences of statements. So something like say negation of P and Q is equivalent to negation P or negation Q. All this kind of equivalences are familiar to us, but here we are discussing about open statements. So it contains variables. And let's consider two open statements P of x and Q of x, and they are said to be equivalent if for any replacement of x, the corresponding if the corresponding statements are equivalent, then the open statements are said to be equivalent. That is, if P of x and Q of x are two statements, then if we replace x with a, then both in P and Q, then the resulting statements are equivalent for all choices of A from the universe of discourse. Then the open statements Q of x and P of x are said to be equivalent. And if P of A implies Q of A for all choices of A, then P of X is said to be implies Q of X. P of X implies Q of X. So P of X is equivalent to Q of X if P of A is equivalent to Q of A for all choices of A from the universe of discourse, and same is the case with the equivalence relation. And also observe that if you have a statement P of xy and Q of xy which contains two variables, then they are said to be equivalent if for all possible choices of x and y, P of AB is equivalent to Q of AB for all possible choices of A and B from the universe of discourse, then the statements Q of xy and P of xy are said to be equivalent. So that's the concept. Now, the logical equivalent or implication of quantified statements in one variables. These are some uh, primary equivalence relations which can be proved in simple methods. So let us consider there exists x p of x and q of x. That implies there exists x p of x and there exists x q of x. So if there exists one x in the universe of discourse which satisfies both p of x and q of x, then we can conclude that there exists x which satisfies p of x and there exists x which satisfies q of x. And let's consider this another one. For all x p of x or for all x q of x. For all values of x, p of x is true, or for all values of x, q of x is true. That implies for all values of x, p of x or q of x. So for all values of x, p of x is true, or for all values of x, q of x is true, which means for all values of x, either p of x or q of x is true. That's the maximum we can conclude, and these two are merely implications, and they are not equivalences. And the second and third equations or expressions are equivalence expressions. There exists x p of x or q of x is equivalent to there exists x p of x or there exists x q of x. There exists x p of x or q of x is equivalent to there exists x p of x or there exists x q of x. And for all x p of x and q of x is equivalent to for all x p of x and for all x q of x. So when we look at this equivalence statements, um, okay, it is a set of symbols, symbolic representations, and to make it somewhat friendly, I think it's better to go through some examples, and we will cover it in our next session, which contains some examples on existential quantifiers. So before that, I request or I ask you to recommend to go through some cases or some examples which illustrate all these four equivalence relations between logical statements. Now, rules for negating quantifiers. So, negation of for all x p of x is negation of the statement negation of for all x p of x, that is for all x p of x is for all values of x p of x is true. Its negation is there exists x negation p of x. So in the same way, negation there exists x p of x is equal to or equivalent to for all x negation p of x. So if you make a statement like um, for all x square is positive, that's a statement. This statement is p of x. Then its negation is there exists x negation p of x. There exists x for which x square is not positive. That's a negation. So for all x p of x, its negation is there exists x negation p of x. It is negation p of x. This is our p of x. Then this one is our negation of p of x. So that is how we negate a quantified statement. For all x p of x is true, the negation for while negating the statement, we are looking for a single x. There exists x, at least one x, for which the statement p of x is false, and vice versa. And there is this is something which is more general, not exactly related to the quantified statements. Here we are dealing with a statement like P implies Q, the conditional statement, and in related to the conditional statement, we can have or we can define a few other conditional statements which are closely related to the given conditional statement, and they are, first one is contra-positive. If P implies Q is a conditional statement, then negation Q implies negation P is known as its contra-positive. Then if P implies Q is a given statement, then Q implies P is the converse of the conditional statement. Then negation P implies negation Q, just taking the negations on the premises and hypothesis at the same time. What we get is known as the inverse of the given statement. Then the only thing we have to aware is if a conditional statement is true, so is the contra-positive. So if the conditional statement is true, then the contra-positive is true. The converse may not be true. That is, I may be familiar to it. The converse may not be true, and same is the case with the inverse. So the truth value of conditional statement, if it is the has a truth value of 1, Then the contra-positive is also has a truth value 1. Okay, anyhow, uh, if a statement is given, then how we can write the contra-positive, the converse, and the inverse. That's an important thing. The converse is important. The contra-positive is true as the if the given statement is true, so that both have the same truth value. So that give an important method to prove a theorem in mathematics. Instead of proving the statement P implies Q, we can look at the truth value of the statement negation Q implies negation P. So proof by contra-positive. So that's a strong method to prove a result. Then in most of the mathematical problems, the first question, if where we state a result, the first question is whether the converse is true or not. So these expressions or these terminologies are important, and we will discuss or we will go through some problems related to this contra-positive, converse, and inverse of logical statements. And now the universal specification and universal generalization. If for all x p of x is true, then p of a is true for all elements in the universe. That's an obvious thing, but that is known as the universal specification. And universal generalization is if p of c is true for any arbitrary chosen element from a universe, then for all x, p of x is true. So that is actually it is nothing but the definition of existential universal quantifiers and the fundamental logic. But anyway, these are universal specification and universal generalization, and these are the concepts which we have to discuss in this session. And we will in our next session we will go through some uh, examples to illustrate the concept of existential quantifier and illustrate the implications and equivalences of existential quantifier, and how we can uh, negate an existential quantifier, and after that how we can form the contrapositive, converse, and inverse from a given statement or conditional statement. All this will be discussed in our next session, and for the time being, we will stop here, and thank you.